Thanks very much for the invite. And I will try to make this not too technical, at least at first, so as not to scare everyone away. I know people are not necessarily very familiar with C-star algebras here. So what is a C-star algebra? It's an example of an operator algebra. Operator algebras came out of quantum mechanics because people wanted some mathematical model to take care of non-commutative behavior that people saw at the quantum level. And these first appeared back in the mid-30s and 40s by a series of papers by Murray and von Neumann that I think it's about 5 papers, 4 of which wound up in the Annals, where they studied self-adjoint subalgebras of bounded operators on Hilbert space that are closed with respect to the strong operator topology. And then later, Gelfand and Naimark studied ones that are instead closed with the operator norm topology, and those are what we now call C-star algebras. So closing in the strong operator topology, that would be a von Neumann algebra. Those are related, but we're going to be mostly concerned with C-star algebras here. So more technically, a C-star algebra is just a Banach algebra. It's got a conjugate linear involution, hence the star. And its norm has to satisfy the so-called C-star equality. So we want that A star A, the norm of A star A is always equal to the norm of A squared. And this seemingly small requirement actually makes these things very tractable compared to your average Banach algebra or Banach star algebra. So some easy examples. If you take the n by n matrices over C, you can equip that with the adjoint as the involution, and the operator norm, which is just given from you here, probably reminds you of classes, maybe if you took a Hilbert space class or something, you would have come across this. More generally, we can do bounded operators on any Hilbert space, not necessarily finite dimensional. And again, you're going to equip it with the adjoint operator and operator norm. And in fact, any norm closed self-adjoint subalgebra, B of H, is also a C-star algebra, and we call these concrete C-star algebras. So the definition at the top is an abstract C-star algebra. This is a concrete C-star algebra. It wasn't clear at first that these two things were the same. Another typical example are commutative C-star algebras. So you take X to be a locally compact Hausdorff space. Your involution is just going to, so you're going to look at functions vanishing at infinity on that space. Your involution is just taking the complex conjugate. Can people see this okay, or should I turn off some lights maybe? And we equip this with the supremum norm. Okay, so here is our picture of our C-star land. On the one hand, we have things like matrices. This is very linear algebra. On the other hand, we have C0 of X, where we get a lot of topological concepts coming from. And most C-star algebras are somehow in the middle. But it's useful to take your intuition from these things. So in fact, we can make this more precise, that this coast really is a coast in the sense that whenever we have a commutative C-star algebra, then there is some locally compact Hausdorff space such that A is star isomorphic to continuous functions vanishing at infinity on this space. And our C-star algebra will be unital precisely when X is compact. And this is really functorial, so if we have 2 compact Hausdorff spaces and any continuous map, phi from X to Y, then this induces a star homomorphism in the opposite direction between the function algebras, just given by precomposing with little phi, and vice versa. So whenever you have a star homomorphism of 2 commutative C-star algebras, this induces a continuous map at the level of the spaces. So this is a duality between the category of compact Hausdorff spaces with continuous maps and the category of unital commutative C-star algebras with star homomorphisms. And if you want to, you can say something similar for the locally compact case, but most of my things are going to be unital, so we'll just sweep that under the rug for the moment. And this is why you often hear C-star algebras described as non-commutative topology. In the similar way you've probably heard non-commutative geometry. At various other Calista conferences, we think of this as non-commutative topology. Okay, so returning to concrete C-star algebras, I said a couple slides ago that this is just going to be a norm-closed subalgebra of bounded operators on some Hilbert space. Whenever we have a C-star algebra, we can talk about a representation of a C-star algebra. What this means here is we have some Hilbert space and a star homomorphism from A into the bounded operators on that Hilbert space. And we say that a representation is faithful if this pi is injective. So in particular, if we have a faithful representation, then our C-star algebra is isomorphic to a concrete C-star algebra. And it just so happens that C-star algebras have a lot of representations, and one can show that, in fact, every C-star algebra is star isomorphic to a closed self-adjoint subalgebra of B of H for some Hilbert space H. So in fact, indeed, concrete C-star algebras and abstract C-star algebras are indeed the same. And using representations, one can construct many more examples of C-star algebras. So here's our C-star landia again. So this really is the commutative coast over here. Everything commutative looks like this. Okay, so those are pretty simple examples, depending on how simple you think topological spaces are. I guess they're not so easy. But we're concerned more about what happens in land here. In particular, what kind of things lie in between these two coasts. And so this is where C-star algebras are very nice. One of the great things about them is that you can use them to encode other mathematical objects, which allow us to study these objects using our C-star algebraic toolkit, which is quite robust. So we saw that, for example, we can study topological objects as function algebras. Algebra is much easier than topology. So what we do here is we have our little C-star machine, we throw in something, the machine spits out a C-star algebra. So we can throw in lots of things like directed graphs. We get a graph C-star algebra. We can throw in groups. We get group C-star algebras. We can throw in dynamical systems. We get cross products. We can throw in foliations via groupoids. We get groupoid C-star algebras. We can throw in a vector bundle, and we can make some so-called Kunz-Pimsner algebra. Of course, not everything works. If you try to throw in a cactus, it's going to just spit it out. If you try to throw in a Pilsner, then autocorrect really wants to make this work, so we get these things called Kunz-Pimsner algebras. Okay, so part of my talk was graph C-star algebras, so let me tell you what I mean by a graph. In particular, I want a directed graph. So this is going to be a four-tuple consisting of two countable sets. So E0 we're going to call the vertices of our graph E. E1 is the set of edges of E. And then we have these two maps R and S, the range and source maps, which are just set theoretic maps from the edges to the vertices. So we identify this data with a graph in the obvious way. So here we have a graph. Our vertices are indeed going to be our vertices from the graph, so we have 5 of them. Our edges, I've labeled them here from E1 to E8. And what do the range and source maps do? Well, they do the sort of obvious thing. The range of an edge is the vertex it points to, the source is the vertex it's coming from. So for example, if we look at the range of E7 here, we're going to get V5. And if we look at the source of E1, that's coming out of V1, so we get V1 there. And so note, for example, that we're certainly allowed to have multiple edges coming in and going out of each vertex. And I did say these can be countable, so indeed we can have infinitely many vertices. We can have infinitely many edges between vertices. So we're going to throw that in and get a graph C-star algebra. So how do we do this? Well, we construct a universal object, which is generated by pairwise orthogonal projections. So for those of you not familiar with what that means here in the C-star context, it means an element that is the same as its adjoint and its square. So this is exactly what you think it should be in matrices, for example. And then and orthogonal, I just mean P and Q are orthogonal if P times Q is 0. We have partial isometries. What does this mean? It means that when we take S star S and SS star, we get projections. And we throw on some relations. So we want that whenever we have two distinct edges, taking SE star SF is going to be 0. If we take SE star SE for a single edge, it's going to spit out the projection of the range. And if we take what's called the source projection, so SE star, this is going to be a sub-projection of the projection corresponding to the source. So by sub-projection, I just mean that if we have P, Q projections, then P is less than Q if P times Q equals Q times P equals P. And when it makes sense, we can describe the projection corresponding to a vertex in terms of things that are going out of that vertex by summing up over all the edges that are exiting that vertex, but only when this makes sense. So obviously it doesn't make sense if there's nothing leaving, and it doesn't make sense if there's infinitely many. So these do contain redundancies, but it's useful to think of them all, in my opinion. Okay, so graph C-star algebras are very nice because not only can we use our C-star toolkit to say stuff about the directed graphs like we saw with the C-star machine, but we can also see many properties of the C-star algebra by just looking at the graph itself. So for example, you can immediately tell whether or not A is unital. This will happen exactly when it has finitely many vertices. You can tell its ideal structure. That's a little bit more complicated to describe, but it's certainly possible. You can tell some fancy C-star properties like stable finiteness or infiniteness, which won't be so important for this talk, actually. So basically, if an infinite C-star algebra means you have projections that behave funny in a Banach-Tarski kind of way, in the sense that you can find subprojections that are, you can twist one into the other, but you can always subdivide them infinitely many times. That's kind of vague, but it's not super important. And also it's K-theory. So again, we like to think of C-star algebras as non-commutative topology. We import ideas from topology into the non-commutative world. C-star algebras has a notion of K-theory, which in the commutative case gives you topological K-theory. So we can now associate K-theory also to a non-commutative C-star algebra. It's not going to be a group in general anymore, but it's not going to be a ring, but it will still be a nice abelian group. And furthermore, even ideals and quotients of graph C-star algebras are again graph C-star algebras. And if I identify where the graphs are where the ideals are in my graph, I can write down what the ideal looks like in terms of a graph and what the quotient looks like in terms of a graph. So here are some examples that are not so difficult to check. So if we take just a straight line with n many vertices and just arrows in one direction, we're going to get n by n matrices on the complex numbers. And this is actually quite easy to check if you say just look at M2. So if you get bored, that's a fun little exercise. Another nice example is this guy here. So now we have one vertex, so we're just going to have a single projection. Which is corresponding to our vertex V. And then we have an edge. Oh, these are all very wet. So we're going to get that And it's easy to check that this projection will act like a unit on everything because it's just got these two generators. And from this, it's clear that this guy here is going to be a unitary. So we're getting a commutative C-star algebra generated by a unitary. We're going to get continuous functions on the circle. There are some more, slightly more difficult examples. If we were instead to attach n many edges to a single vertex, then we get this funny behavior of projections. We get something called the Kuntz algebra, which is well studied in C-star algebra theory. But again, we won't be saying too much about these funny infinite guys. Now, another nice thing about graph C-star algebras is that they are classifiable in a sense. So my day job is a classification of C-star algebra person, and what we try to do is classify C-star algebras by reasonable invariance, like K-theory, for example. And when you have a simple graph C-star algebra, you can see that it's going to be either an AF algebra or a Kirchberg algebra. So Kirchberg algebra, that's just one of these funny infinite guys. AF algebra is going to be an inductive limit of finite dimensional C-star algebras. Finite dimensional C-star algebras are just direct sums of matrices. Now, AF algebras, these were classified by George Eliot back in maybe 1990 or so, and he showed that they're isomorphic if and only if this so-called ordered K0 group is isomorphic. And these Kirchberg algebras were also classified up to isomorphism by K0. So all simple graph C-star algebras are covered by existing classification theorems. So what is this ordered K0? Let me just mention it briefly. If we have a C-star algebra A, then we look at equivalence classes. So you start with projections in all matrix algebras over your C-star algebra. You put an equivalence relation on this called Murray von Neumann equivalence. This just means that there's some partial isometry that can map between your two matrices. You can equip this with addition by just putting things down the diagonal in some higher size matrix. This makes it into an abelian semigroup, and now we take the Grothendieck completion of these formal differences. We can also, in many cases, put a nice order structure on this by equipping it, by defining this positive cone in K0 of A, and just saying that x is less than y if x minus y is in the positive cone. So this is what goes into the these are the needed things for classification of approximately finite C-star algebras. Now, if simple graph C-star algebras are either AF or Kirchberg, these are classified just by K-theory, which is a nice computable, in principle, countable thing. We might want to try to classify non-simple graph C-star algebras. So we already saw an example. C of T is far from simple. It has many, many ideals. Right, yeah, every ideal is of this form, so there's, it's far from being simple. And in general, classification results for non-simple C-star algebras are just going to be way too complicated. I mean, this would amount to being able to classify compact Hausdorff spaces, for example, in a reasonable way, which is you're not going to be able to do by some nice countable object. But if we're asking for a C-star algebra that isn't so far from being simple, then maybe there's some hope. So for this, we want to look at the primitive ideal space of a C-star algebra. So whenever you have a star representation, you can ask if it's irreducible. This just means there's no non-empty proper subspaces. And in the commutative case, every irreducible star representation up to unitary equivalence is just going to be evaluation at a point. So the primitive ideal space we define to be the kernel of irreducible, the points are kernels of irreducible star representations. Now the kernels are going to coincide whenever your two irreducible representations are unitary equivalent. So in particular, the primitive ideal space of a commutative C-star algebra is going to just be indexed by the points in C of x, in x rather. So this will, this is essentially like the, right. So then you equip it with the Hull kernel topology, which is essentially like the Zariski topology, I guess, for those of you that are familiar with that. Okay. So there's this very nice theorem that says unidal graph C-star algebras are in fact classifiable by some invariant. So this invariant is basically K-theory, but it's a bit of a mess because you do need to consider all of the K-theory of all the ideals in your graph C-star algebra and how these things all fit together. So you get all these maps. I think when they were first coming up with this, they called it like a K-web or something, which is sort of appropriate because it does kind of look like a web. So here are some more examples of graph C-star algebras that are not necessarily simple, but which we now know can be classified. So these are due to Hong and Szymanski. What are they? Well, these turn out to be quantum odd-dimensional spheres. So for example, you can imagine what CQ S9 would be, CQ S11, et cetera, and I'll say what this mysterious notation means in a moment. Quantum complex projective spaces, they also drew some graphs for. Here they are, so again, you can iterate this for any n. Sophie Zegers, who for a while was a postdoc with us in Prague, she showed that this was the, quantum symplectic 7-sphere. And you might notice that this looks an awful lot like some of these other spheres. And indeed, one can see immediately from the graphs that it turns out that the quantum symplectic 7-sphere is going to be isomorphic as a C-star algebra to the relevant odd-dimensional sphere, quantum sphere. There's also things called quantum lens spaces, quantum weighted projective spaces, quantum teardrops. So this is when I come to the second object in my title. What do I mean by a quantum space? So this is going to be a bit hand-wavy, but usually it refers to some sort of Q deformation of a function algebra on a classical space, which can be represented by generators and relations. And what you do is you take a Q between 0 and 1, and you replace the commutation relations with some relations that now involve generators and functions in Q. So here's an example. The 2 torus is just going to be the C-star algebra generated by 2 unitaries that commute, right? Okay, so U and V are unitaries and they commute. Now, if we take some Q, then instead of asking U and V to commute, we can throw in this e to the 2 pi I Q here. And we call this the non-commutative 2 torus. And the key is that when Q is equal to 1, we get back the original commutative torus. Similarly, one can define the non-commutative n torus, and these are very well studied in the theory of non-commutative geometry and quantum groups. Another well-known example is the non-commutative 3-sphere. So here we have a C-star algebra that's generated by alpha and gamma, subject to the relations that this is a unitary matrix. So we see the Q appearing here, and you can check that if Q is equal to 1, you're just going to get the usual sphere relations for functions on S3. Now, compact connected, simply connected Lie groups and their homogeneous spaces. For example, things we've seen before, the odd-dimensional quantum spheres and the quantum complex projective spaces. One can do this in a very precise way that really allows one to keep the Lie theoretic flavor of these objects. So for example, just like in the classical setting, the Q spheres, odd-dimensional Q sphere, admits an action of the circle, and one can recover quantum complex projective space as its fixed point subalgebra. For n equals 2, this is the well-known Podlish sphere, which again is one of these objects that's very well studied in quantum groups and noncommutative geometry, which is a Q deformation of the 2-sphere. Now, these quantum projective spaces, they're examples of a larger class of spaces called quantum flag manifolds, which in the classical setting are just simply connected, compact, homogeneous Kähler manifolds. So in particular, they arise as quotients of simply connected, compact, semi-similar Lie groups. And these Lie groups admit a particularly satisfying Q deformation by looking at their enveloping algebra of their associated complex semi-simple Lie algebra and Q deforming that. So here, if we have a complex semi-simple Lie algebra G, we can Q deform its enveloping algebra, and this behaves a lot like the usual enveloping algebra. In particular, it has a Hopf star algebra structure, and it will have the same representation theory as the undeformed enveloping algebra. So if we have a rank R Lie algebra, then what is UQ of G? It's going to be generated by these elements EJ, FJ, KJ, where J runs between 1 and the rank, subject to some ugly relations that you should not try to digest right now, and some things called the quantum Serre relations. Whoops. And we could put a Hopf algebra structure on it. Again, I don't expect you to take these in. I guess the main point is that you can imagine that when Q is 1, hopefully everything works out nicely and you get something you already know. By adding the star, we refer to this as the compact real form of UQG. Now, as I said, those are all really ugly relations that I would not expect you to take in a quick talk. But the point is that these can actually easily be read off the corresponding Dynkin diagram. So the Dynkin diagram will contain all the information necessary to write down these relations. Now, there's a Hopf star algebra dual of the quantum enveloping algebra, which we call the quantum coordinate algebra. This is also a Hopf star algebra, and it also admits a C star completion. So we can equip it with a C star norm and complete that and get a C star algebra. And when Q is equal to 1, we get exactly continuous functions on G, where G is the simply connected compact semi-simple Lie group whose Lie algebra was G. So this fits nicely into this framework of sort of Q-deformed spaces. Now, the C-star algebra will no longer be a Hopf algebra because some of the Hopf algebra maps aren't bounded, so they won't extend to the C-star algebra. However, we always get the coproduct, and you can check that this will give us a compact quantum group in the sense of Voronowicz, if you're familiar with what those are. So these are, the C-star analog of a lot of things that are studied in Hopf algebra theory. Okay, so here's an example. Take SL2. The Dynkin diagram is just a single node, which means the quantum enveloping algebra is just generated by 3 elements, E, F, and K. And its dual turns out to be generated by an alpha and gamma, subject to the relation that this is a unitary matrix. So this probably looks familiar, and indeed we see that just as in the classical picture, we get this isomorphism between quantum SU2 and quantum S3. This holds at the level of both the coordinate algebra and its C-star completion. So how do we go about constructing a quantum flag manifold, which is a particular type of homogeneous space? So we take a Dynkin diagram, and we're going to choose a subset of nodes. This allows us to define a subalgebra in the quantum enveloping algebra, which is just going to be generated by all of the KJs for the rank of G. And we're just going to throw in the EJs and FJs if the jth node is in our chosen set of nodes. This inclusion dualizes to a surjection and allows us to construct a right coaction of OQG, of OQLS on OQG. And we can look at the fixed points, the co-invariant subalgebra. This, again, this is going to be a C star, the subalgebra of OQ of G, so we can complete it with respect to the norm of OQG. This gives us a C star algebra. And again, when Q is equal to 1, we get the continuous functions on the associated classical flag manifold. So for example, quantum projective space, we can write it as this homogeneous space. For this quantum version, we cross our first or last node on the AN Dinkin diagram, and our set S is going to be the stuff that remains. In principle, we could calculate generated relations for these guys, but it's usually very tricky and is much more trouble than it's worth. It's not so bad for quantum CPN, but even as soon as you move to Grassmannians, it gets quite unwieldy quite quickly. However, for us, from the graph C star algebra perspective, fortunately, we don't need to worry about that. We have another way of constructing these C star algebras. So to each Dinkin diagram, we can, of course, also associate the Weil group. This is just going to have one generator Si, subject to the following relations. So every Si squares to 1. Si, Sj are going to commute if there's no edge between the nodes. And it's Si, Sj to the cubed. It's going to be 1 if there's a single edge. To the 4 is equal to 1 if it's connected by 2 edges. And to the 6 if it's connected by 3 edges. Okay. So it turns out that this Weil group is very much associated to star representations of the C star algebra. So for every I less than the rank of G, or equivalently every node on our Dinkin diagram, we get a map from UQSL2 to UQG, which just maps the generator of UQSL2 to the relevant generator that you've indexed by that node. So with the dual picture, we get a surjective star homomorphism, which allows us to define a star representation of CQG as follows. By composing it with this infinite dimensional star representation of CQSU2. So it's quite interesting that, well, CSU2 certainly does not